Previously, you learned about the mind-blowing, mind-boggling thing that electrons, we thought they were particles, but actually they are also waves. So, this is an atom here. And instead of thinking of electrons going in and out, maybe on this level, the next level, or in the largest orbit outside here, now to remember that, actually they are waves. And you can only be on certain levels because that's where you can form a nice stationary wave. So all this we call energy levels. So you see, behind me there's this hiding thing here. What is this? E. That is the energy of the electron if it is at this level. These are called energy levels, and these are what we call bands. So N2, N3, N4, higher energy. That's what we're going to learn about today, energy levels. Let us begin with the case study of the hydrogen atom. Well, you can say the hydrogen atom is isolated, it's by itself, no other atoms nearby. And this is in a low pressure gas form. Okay, so on the atom, you can see the left side is roughly how we look at these things we call shells. I mean, in chemistry, like to call them shells or orbitals. Here we can call them energy bands as well. That's another name for them. So you see this N1 band. This is called the ground state, where the minimum energy an electron can have when it is orbiting around this thing. So maybe if you want to draw a particle, there you go, one particle. Or you want to draw a wave? Sure, you can draw a wave. I don't know, it's a wave and particle at the same time, so up to you, whatever you want to draw. So that would be ground state, the lowest possible energy. How do we know what the energies are? You can see this here, negative 13.59 eV. That's what we call an energy level. So you can go to higher energy, up to N2, 3, 4, 5, 6, all the way up to infinity. Once you break infinity, you're free. The electron is gone. So one question is, why do we study these electron energy levels? Why can't the electron just chill at one level? Well, see, here's the thing. If your electron is in the ground state, something can cause it to get excited. Then you go up. Jumps to the next energy level. Pew! Ever wonder what makes it excited? One way to make an electron excited and jump to higher energy is with a photon. Let's see if we can use this photon to excite the electron or not. Pew, 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 pew. Photon is not absorbed. Electron is still there. Wait, why is that so? Is it not enough energy? How much energy does this need to go up? Let's see. This is 10 eV. I need to go up. Okay, let me give it more energy. Here we go. Higher energy. See? The wavelength is changing. The color is changing. The EV is increasing. Zoom, 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 zoom. How about 4? Let's see. Can you excite, please? And it does not absorb. Why? I give more energy, it doesn't absorb. That means there must be a very specific energy I give to this electron if I want it to jump from this to the next level. So because energy is, all these are discrete levels, that's why we call it discrete. You can only have this energy. Anything in between cannot. So if you want to jump to the next level, you need exactly a certain amount of energy. What is this delta E? This delta E will be E2 minus E1, which is, I guess, negative 3.4 minus 13.59. So you only can have that energy, then only it will excite. So maybe an incoming photon comes in, zoom, 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 with exactly that delta E. Then you can jump up and excite. So it happens that you need exactly 10.19 EV to go from n equals to 1 to n equals to 2. Okay, that's the difference between this number and this number, 10.19. What wavelength is that? That is roughly about 121. I calculated 121 nanometers. Okay, so incoming radiation of this wavelength have this energy come in, then this electron will absorb the photon. So I'll write here, absorb the photon and get excited. So it goes to a higher energy state up here. Woo, more energy. Okay. Then let's try it out with that simulation just now. So for this one, 10 minus 7.5, that's about 2.5, right? So I'm going to adjust until this EV here is 2.5. Let's go 2.8, 2.5. That's close enough. I can't get exactly 2.5. Let's try it. This looks like a bluish green on my screen. Let's send this in to the electron and see if it will absorb and excite itself. And ping! Oh, it got excited. It went up. So it absorbed the photon and get to a higher energy level, which means now it's excited. This is what we call excitation. So remember, the moral of the story is you must have exactly this change in energy coming in from the photon, then only you will absorb and go to the next energy level. I mean, you say, Miss, can go to the next one? Can. You must have exactly the same energy incoming, only you will go up to the next energy level. But the idea is, it must be discrete. So I'm going to write that down on the left side. Orange warning sign. The energy can only be, or the electron, what am I saying? Energy is only discrete. Let me rewrite that thing. Electron, not energy. Energy is in discrete levels, yes. But electron can only exist in specific energy levels. So if you are in the n equals to 1 band, you are there with this energy. Anything in between, cannot. N equals 2, you only can have this energy and you'll be here. If you have a higher energy, you'll be up here at n equals 5. So you're going in and out between the different energy levels. Now you're wondering, Miss, why is this energy negative? Well, 0 is the largest number, right? Here is most negative, lowest. Highest energy, lowest energy. But why is it negative? And also, why this gap is so big between this band? Then it gets smaller, 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 and smaller. To answer that question, you kind of need to remember your electric field a little bit. Oh, let's scroll up and add a note. So this is, let's say, between 1 proton and 1 electron. Does the electron want to go to the proton? Of course, it loves the proton. It's attracted to it. But that's if we're thinking of particles. But in waves, you have a very discrete kind of energy, like we saw down here. But if we assume that we're back to the world of particles, let's say we pretend we forgot, we never heard that there are waves, we're back to particles. How do you find the energy between a proton and an electron? Energy is what we call electric potential energy. Also, the symbol we use is U. How do we calculate this U again? Oh, remember from electric field, U equals to KQQ over R. So this is Q and this is Q. One of them is positively charged, the other one is negatively charged. Hence, this whole graph will have a negative because of this. So your graph shape actually looks like this. So if you go further and further away, for example, you start from the very close. Wow, energy is very negative. Negative what? If you're really close, negative 13.5. Very big negative. But if I go a certain distance further away, my energy gap is a bit smaller. If I go a fixed distance, energy gap a bit smaller. Fixed distance, energy level is a bit closer. Fixed distance, it's pretty much the same line, miss. Another distance, also the same line. So you see the lines are of energy. Let's say this is N1 energy, E2, I'm just going to call it E3. And then E4, E5, E6, they're all just like super close to each other. I mean, eventually you will reach 0, but it's not until you reach the infinite level. So the further you go, the closer the lines get because of this shape of this curve of electric potential energy between the proton and the neutron. Electron. But of course, this graph can get complicated when there's more charges in here. But that's all you need to know. Like, just it's negative because attractive. Okay, this one will always go down to this low part. But also because of the shape of the graph, lines get closer together. Anyway, so that's absorption. The story is electrons can get excited. But they can also go the other way, right? Yeah, probably. If your electron is kind of up here, and it can just say like, I'm tired of being excited. I'm going to de-excite and chill a little bit. So zoom, it transitions down. And what does it do in the process? Where does the energy go? It's going from high to low energy. So it has to emit some kind of energy, well, in the form of photon, with exactly the same amount of energy from this transition, this delta E. Okay, so this thing we can calculate with E equals to HF, you know, frequency of a photon, light, and this will be exactly the same color, 121 nanometers, if you're looking at this one. So when it release a photon, we can say either release or emit a photon. This is what we call de-excitation. The electrons is not excited anymore. De-excite. The electrons de-excite and fall to a lower energy level. So just remember, this one is high energy. Down here is low energy. So you go up, come down, go up, come down. But your energy need to come from somewhere. Now if you notice up here, there's N infinity. Now if your electron have enough energy given to it by whatever means, photon, heat, whatever, then it will have enough energy to go, woo, break free and yeet out of the atom. This is what we call ionization. So your atom has lost an electron. That's if you have enough energy lah. But if you don't have enough energy, you just go like excite, de-excite, excite, de-excite, excite, de-excite, excite. Just bounce up and down between the energy levels. Okay, so let's look at this recap of this idea. So electrons in atoms can only have specific energies. Discrete. Why? Because of the quantum properties that we discovered. And no other values between. So you cannot stay in between. You have to stay on any of these bands. Energy bands. So like I mentioned up here, there's two types of possible transmission. The first one is called absorption and the second one is called emission. So if we look at the case of hydrogen, this hydrogen, there are many possible transitions that can happen. For example, if you look at absorption, you could go from ground to this level, or you could go from this one to N1 to 3, N1 to, I guess, 1 to 2, 1 to 3, 1 to 4 even. Sure, it's also possible. Or you could go from 2 up to 4 to 5. My lines are beautiful. Or you could go from, I don't know, from 3 up to 5. Sure, why not? Or 3 up to infinity also can. So all these kind of different lines, if you put them all together, it's what we call an absorption spectra. A series of colors specific just for hydrogen. And remember, these transitions come with an energy change, and that energy change corresponds to a specific wavelength. So for this one, purple, drop down. Oh, then got a specific wavelength associated with this energy transition. Remember, E, oops, wrong marker, E equals to HF. So here, a change in energy is given, is going to be a photon coming out with a certain frequency or a certain wavelength. Back to the photoelectric effect equation, right? Okay, so remember this one. Other than absorption, what if it's an emission? You absorb, you get excited, you go up. Maybe you are already excited in the first place. So maybe you are somewhere at the N5 level, down up here. Then you're like, I de-excite lah. Can also, you de-excite here lor. Or maybe you want to drop down to here, also can. Maybe like, I de-excite one level only. Can. This is called emission spectra. So in all these cases, once you de-excite, you will release energy in the form of a photon. Look at my nice wave there. Energy come out. You de-excite already, you're releasing your energy. Okay, so photon is out. Or maybe you want to do something different. You're like, maybe I am at N4 in the beginning. And I'm going to drop all the way down to N1. Oh, that's a very big energy coming out. So that one will have a very high energy photon coming out. I'm just going to call this pink color photon. High energy, pew, come out. Sure, because that's a very big transition, so a lot of energy. Or you say, I drop to next level only. Or I drop here only. Sure, all these transitions possible. Maybe you draw one more. No need already lah, can already lah, okay? So the bigger the energy change, the more energetic the photon that comes out. Because a big energy give to photon. Okay, so these are all the electrons transitioning down or up or down, wherever you want to go. Also, forgot to mention just now, if you look on the left side, which one you think needs the most energy to transition? Which excitation you think needs the most energy? You can look and see the biggest arrow. Which one's the biggest arrow? Look at this long one. So this one will need a huge amount of energy. Absorb the photon. Okay, absorb and then only can go up. Okay, that's the idea of absorb, go up, Release energy, drop down. You are the electron jumping up and down. You absorb energy, throw out energy. Up to you. So we're going to write down some notes here to help us remember. In the absorption spectra, there are many possible colors that can come out. They can be absorbed. Could be absorbed the pink color. You could absorb something else, like maybe you need a little less energy. Maybe you need something even lesser, blue color. So different color that is absorbed depends on how much energy is the transition between the bands, the energy levels. So we can say electron absorb photon. Absorption ma. Okay, and the photon will have a certain energy, hc over lambda. So once it absorbs photon, it excites into a higher energy level. There we go. It's a good reminder for us. And the emission is the other way, the opposite. Now you are already excited. So you are up there, excite. Very excited. So what do? You de-excite. So you say electron de-excite into a lower energy level. And what happens in the process? Where does your energy go? You emit it, you throw it out. And emit a photon of corresponding wavelength, which can be calculated with the change in energy, E equals hc over lambda. So that's what wavelength your photon will have once you de-excite. Now I need to tell you one thing. All these colors and lines, all these energy levels, okay, these energy levels are specific just for hydrogen. Other elements will have something else. So let me see if I can find my picture. Ooh, this is a very big one. So hydrogen have all kinds of transitions. Some we can see, it's under visible light, some we cannot see. But all these bands, all these colors are specific just for hydrogen. This here is a picture of me playing with a hydrogen discharge tube, like a lamp. And you see, wow, why got so many color? I mean, the light itself is like bluish, but then you see all kinds of blue, red, other kinds of colors coming in. So these are what we call the emission lines of hydrogen. So just by the color, I can tell what element is this. Then I change to a different light. Wow, what color is this? Got orange, got pink, got green. This is actually a sodium lamp. So sodium different color, hydrogen different color. Everybody got their own color. So if the lines that are emitted are specific for each gas or element, we can use this to study different kind of elements just by looking at their color and what wavelength they emit. So we're going to look at some of the experimental setup. You're like, wow, Miss, how do you get this thing? Let's look at the experiment. So there are two experiments you can do. One deals with absorption and one deals with emission. Let's start off by looking at the absorption experiment. So in this absorption spectra, what the setup is, you have some white light coming in, and then the white light is sent through a cloud or a flask with some cool gas. Cool gas means the gas is just chilling, not excited. Then, after the light goes through the gas, comes out, goes through what we call a prism. This one is to spread out the light or to disperse out the light so that you can see the lines that we saw just now in the picture. Sometimes you use diffraction grating as well. Both also okay. Diffraction grating. So the whole idea is you're going to have a cloud of some cool gas of a certain element, neon, argon, whatever gas. But you send in white light. Now white light has all colors inside. Rainbow colors. There. White light comes in. But when it comes out, some colors might be missing. Maybe only red come out. Maybe a little bit of green. Where did all the other colors go? That is what we have to think about and explain inside here. So what you will see on the other end is a continuous spectrum. Means a rainbow color, but with some missing colors, some missing wavelength. So we call this a continuous spectrum with dark lines. Where did those lights go? Where did those wavelengths go? Now this is the absorption spectrum. See the one down there? You have a continuous color, this whole rainbow down here, but there are some missing lines. Like, why are there dark lines here? What are these dark lines for? How do we explain these dark lines? Well, the answer is they have been absorbed by hydrogen and thrown somewhere else. So they are not here anymore. So if this is our cool gas, hydrogen, everything else comes out except for a few wavelengths that are missing. So most of the colors made it through, but where did blue go? A certain wavelength of blue is missing because maybe it got thrown out somewhere to the side. Pink is also missing a little bit. Why? Why did it only absorb blue and pink? Well, that's related to the energy levels of hydrogen gas. Right? So now we say it will take in only specific wavelength and say, ooh, I like this, excite. So that's how we can describe this experiment observation. So if we want to explain why there are dark lines in the spectrum, okay, dark lines, why are there dark lines? Why hydrogen has done something to it, the hydrogen gas absorbed some of the wavelength. You need to be able to describe this in the past year because they will ask you to describe why are there dark lines. So you can say that when white light passes through a cold gas, what happened to the electrons? The electrons absorbs energy from the photon. This is what we call excitation. Okay, so the electrons will move to higher energy level or transition to higher energy level, and this is what we call excitation. Get excited, move up to higher energy level. That's the first thing I want to say. Then, what about the wavelength? Why only blue and pink? Why not other colors? Why those specific lines missing? That one, you talk about the energy of photon. So the energy of photon, is the same as the difference in energy level. Okay, so that is going back to our original idea up here. Okay, if this photon has been absorbed with a certain delta E, that is the exact same difference between these two energy levels, N1 and N2. Okay, so just nice, absorb, go up. You give me the energy, I can go up to this level. That's what we're trying to say here. So, only specific energy levels can exist, right? So only specific photons can be absorbed. So we're going to talk about that as well. So since the energy, I'm going to say E levels, since the energy levels are discrete, means only a certain energy. So the light of a particular wavelength is absorbed. Only that wavelength for that energy level. Okay, so the idea is discrete. So one wavelength for one jump or transition between energy levels. Okay, let's see what else next. So we talk about, okay, it absorbed those lines only. Then what happens after that? Wouldn't the electron de-excite eventually? Yes, it would. So you can say when the electron de-excites, excited already, now drop back down. Where does it throw the photon? It releases or emits the photon in all of photons, because there's many electrons, right? So when electrons de-excite, it emits the photon in all directions. Simply throw everywhere instead of the original direction. Okay, and this will create a lack of that photon in your emission when you're trying to observe it. So creating several dark lines on a continuous spectrum. Ooh, look at this story. Can tell this story or not? The main idea. Okay, number one, electrons absorb. So they move to higher energy. Okay, and the energy levels are very specific. So whatever energy the photon has, that is it, lor. The difference between the energy level. So say for example between E final minus E initial, where you are, and then you go up to wherever you are next. Okay, and then once you de-excite, you throw the photons in all direction instead of the original destination, so you won't see that. That's why there's dark lines on the continuous spectrum. So that's what this picture means. White light come in, some absorbed, only a few get through, but some of the wavelengths are missing and it's thrown in all kind of different directions, except where it's supposed to go, which is on the screen, where we want to observe it right here. Okay, so this is what we call the absorption spectrum, where we send light to a cold gas and we see what are the wavelengths that made it through to the screen. But there's also another type of method we can study this spectrum, and that is using a hot gas. So this one is cold gas, we shine light. Who is missing? Already absorbed by the gas. But you can also say, what if I just have a hot gas just emit the photons? Yeah, then you have what we call an emission spectrum. How does that work? Let's look at the second experiment. So here, instead of white light into a gas, you just have a discharge tube. Ooh, what is a discharge tube? A discharge tube is a container that has hot gas inside it. So gas of a certain element, maybe let's say neon. Neon gas inside there. It's already excited in the first place. So what I do, when it emits light, it's already of a certain combination of wavelengths. So all you need to do now, lesser steps, is to put a prism here or a diffraction grating. To do what? To disperse the light. Spread out so you can see the difference. What am I saying? Disperse the lines of emission. So you can see it on the screen. Emission lines. So what you will see is actually something different now. You won't see a whole rainbow. You will only see what wavelengths are coming out of this discharge tube. Okay, so if it's only these 4 lines, that's it, these 4 lines. So we can call this just colored lines against a dark background instead of a continuous spectrum with dark lines. So it's a little bit different here. So what example you can look like is this one. No? So this is a discharge tube. The colors you see are just the lines from this discharge tube. And this picture was taken through a diffraction grating. Okay, same for this one. Wow, look at all the colors, okay? Whatever comes through, those are all the wavelengths that are emitted by this sodium lamp. But how does a sodium lamp even emit stuff in the first place? Let's go back to this. So this sodium lamp already has excited hot gas. So inside there is something like this, just a glass container. You have an electrode, negative, positive. And this one is very low pressure, so like vacuum, almost vacuum. But you're going to put like, let's say neon gas or hydrogen gas inside here. Hydrogen. So once you run electricity through this gas at certain potential difference, V, and certain pressure, okay, almost vacuum, low pressure, then suddenly the hydrogen gas will start to conduct electricity. So it will start to emit all kinds of light. Ooh, so this one will kind of like pink come out. Maybe also got light blue, which is the other characteristic wavelength. Wow, got blue come out, pink come out, all the colors. But all these colors are specific to hydrogen. So it basically excited gas inside the tube. And it's just emitting. That's your discharge tube, and that's how it works. And you might have seen some of them in science. They're very colorful. They look like lightsabers. Photons, basically. Helium has a certain color. Neon, a bit orangey. Argon, purplish. Krypton, a bit white. Xenon, bluish, whitish kind of colors. So that is how we can see this experiment. Okay, discharge already have a few wavelength, so you only see those few lines over there. So that will be this picture right here. Now this is correct. So how do you know it's hydrogen? Hydrogen will only have these wavelengths. 1, 2, 3, 4. Helium, only these ones. Mercury, oh my goodness, look at uranium. So many lines on its spectra. Is emitting a lot of different photons of different energy, because it has many energy levels. Okay, so how do we explain this thing if we ever have to write this in the past year? Let's settle down and try to write. How would you explain why on the screen you see colored lines? Why? So in hot gas, you can already say that the electrons of this gas atom, whatever that is, electrons are already at higher energy levels. So they're all very excited already because of potential difference or something else. They're just excited there. So what they can do is they can de-excite. So during de-excitation, let's go for space here. What happens? What do they do with their energy? You can say that the electrons release energy in what form? In the form of photons. And these photons have a very specific wavelength because they are transitioning from one energy level to the next one. So they have to have only that level. So maybe you go from here, n equals to 3, you drop down to n equals to 2. Okay, as you de-excite, you release a photon with a certain energy that is exactly the same as the energy difference between these two levels. That's just what it means. Okay, so they release energy of specific wavelength, and this wavelength corresponds or corresponding to a colored line on the whole spectra. Why do you use American spelling? Okay, so you come down, specific wavelength come out. Maybe this one is orange color. Okay, sure, orange color come out. So you will see an orange line on the whole spectra. Now, what next? So let's talk about the orange line. So each line on the whole spectra, each line corresponds to a discrete energy, such as the delta E over here between N3 and N2. So discrete energy change. And what does this imply? Implying that your atom has discrete energy levels. So I'm going to say implying discrete energy levels. There we go. What else can we talk about this? How to explain the colored lines? Well, we can just restate the question one more time. And we said that, so all these are what we call emission lines in the spectra. And all these emission lines correspond to specific wavelengths that are observed. So these emission lines, emission lines that correspond to specific wavelengths are observed. And this is for hydrogen or whatever gas that you are putting inside the discharge tube. All specific. Okay, so to sum up this explanation, in the beginning, electron already excited. So when they de-excite, they release energy in the form of photons. And each photon has a specific energy which correspond to this difference in energy level. Okay, and this is what we call all the emission lines lah. Right? They all have specific wavelengths. So yeah, that's our emission spectrum. So make sure you know how to tell the difference between both. Why are they dark lines again? Well, this one, dark lines, absorb. The gas absorbs some of the wavelengths that correspond to its energy levels. So between N1 and N2, for example, there's an energy difference there, which was, what did we calculate it? 10.19 eV, okay? And if you're using a discharge tube method, then you are only emitting specific wavelengths that correspond to energy level. So I'm going to write that down, a reminder. Whatever is emitted, well, this one is energy of photon, is also the energy of MJ between levels. So E final minus E initial in a transition. And that equals to Hc over lambda. This kind of summarizes everything, but you need to be able to describe it in words. So that's all for this video. I'll see you in the next bonus video, short and sweet, on the applications of this idea of emission and absorption.